So here's what makes weak acids way more difficult than strong acids, okay? And weak bases way more difficult than strong bases, okay? What makes weak substances way more difficult is they don't fully dissociate. So with a strong acid, if I know the acid concentration, I know the H plus ion concentration, right? But with a weak acid, I don't know how much it dissociates. I can't do that. So what we actually need to do is we need to write a mass action expression, and we need to know the equilibrium constant for how much these acids dissociate. So if I was going to write a generic mass action expression, which we're going to do right now. All right. So if I'm going to write a generic expression here, so let's say we have a weak acid, we'll call it HA or HX, and we add it to water, which is a pure liquid. It's going to donate a hydrogen. It's going to make hydronium, H3O plus. And you're gonna get the conjugate base, A minus. Cool. Now, if I go to write the mass action expression, remember, pure liquids and pure solids don't go into the mass action expression. So this is going to be the equilibrium constant equals the H plus or H3O plus, doesn't matter what you call it, times the conjugate base over the original concentration of the acid. So this is just a mass action expression like we were doing in the equilibrium unit. Only now we don't call it an equilibrium constant. Since this is the equilibrium constant for an acid dissociating, we call it a Ka. And that stands for acid dissociation constant. Acid dissociation constant. So what we have to do if we have a weak acid problem, we have way more work. If I tell you the concentration of a weak acid, well, that's an initial concentration, which means ice table. And then you got to plug it all into the mass action expression, and hopefully you can make the X a small assumption. And it's, oh my gosh, right? It's like craziness. Let's practice before we do a full-on problem. Let's practice writing some mass action expressions or some equilibrium expressions. So can you write the equilibrium expression for HF? Why don't you try that? Then this is where you got two options. So let's do the HF one first. I'll make myself some room. So here are your two options. You can do it the hard way or the easy way. Let's start with the hard way. The hard way is we're going to write everything out. We're going to put that in water. That's going to give us H3O plus, F minus. Water doesn't go in, so the first way we could get H3O plus times F minus over HF. Like that. Here's how I personally do it, though. I don't show water. I'm lazy. So what I do is I actually wouldn't write that, although this is the 100% correct thing. This is what actually happens. It gives it, because remember, H plus doesn't exist. But I'm lazy. I will usually just write HF dissociates into H plus and F minus, and then I just have an H plus up here. And I don't bother showing water. Either way is fine, because if you're a self-respecting chemist, you need to know H plus is really H3O plus. So you could write the expression like that. I think that's faster because it's just like, okay, that's the full acid and it breaks up into H plus and F minus. Why don't you try it with HClO? So what would be the mass action expression for HClO? All right. So that dissociates into H plus and ClO minus. If I was going to write this, I would be lazy. I wouldn't show water. So I would just write Ka equals H plus times ClO minus over HClO, just like that. I would write that. So there's our mass action expression. Now, what do these constants tell us? Well, they tell us the same thing as the equilibrium constants. The greater the value, the stronger the acid, the more dissociated, right? The more it favors the product side. The smaller the Ka value, the less it dissociated, the weaker acid it is, the more the acids stay together. and didn't break down. So let's try this one. The Ka for HF is 3.5 times 10 to the negative fourth. The Ka for hypochlorous acid, HClO, is 2.9 times 10 to the negative eighth. Which one of those is the stronger acid? Think about it for a second. So obviously HF is the stronger weak acid. Again, it sounds like an oxymoron. Okay, but this is a bigger value than that. Negative fourth is bigger than negative eighth. So this is the stronger acid of the two. Now, if you're not good with scientific notation, right, which is why the pH scale was invented, you could take the negative log of the Ka values, and the one with the lower, what's called pKa, is going to be the stronger acid. I'll show you. So just like pH was negative log H plus, the pKa is the negative log of the Ka. So if we take the pKa's of these values, if I take the negative log of that and the negative log of that, the negative log of 3.5 times 10 to the negative fourth, that's a pKa of 3.46. And then the negative log of 2.9 times 10 to the negative 8, that's a pKa of 7.54. The lower the, just like pH, the lower the pH, the stronger. The lower the pKa, the stronger. So if you're not good with scientific notation, that is an option for you. When you take organic chemistry, they'll usually, or biochemistry, they'll usually give you the acidity of functional groups and pKa's. The lower the value, the stronger the acid. Awesome. All right, folks, we're going to do it. You're going to need about 3/4 of a sheet of paper to do this bad boy. I would like to calculate the H3O plus ion concentration of a 0.1 molar hydrocyanic acid solution. If the Ka of hydrocyanic acid is 4.9 times 10 to the negative 10th, I then want to turn it into a pH, but we'll get there. Oh boy. This is what it's all been leading up to. Here we go. We are starting with hydrocyanic acid, which is a weak acid. It's not going to fully dissociate. You can see that from the Ka value. It's a pretty crappy acid. Times 10 is a pretty weak acid. And I would like to figure out when it does reach equilibrium, how much H plus ion is it going to produce? Not much, but how much? It's not going to produce much. How much is not much? So the first thing you want to do when you get a problem like this is write the dissociation equation. So it's kind of like there's like a stepwise process. So we want to show HCN acting like an acid. So again, I'm lazy. I don't include water. That's going to break up into H plus and Cn minus. Once we do that, we can write a mass action expression. So like step one, dissociation equation. Once you have that, now you can make a mass action expression. So the mass action expression is going to be Ka equals the H plus ion concentration times the cyanide ion concentration, Cn minus, divided by the HCN concentration, just like that. And then once you have the mass action expression, now we can make our ice table. So it's just like back in that unit 13, right? It was like mass action expression, ice table. Well, now it's like dissociation equation, mass action expression, ice table. So now we set up an ice table. So again, everything that's in our mass action expression gets a row in our ice table. Okay. So we're gonna write ice. And we're gonna get 3 rows in our ice table. We're gonna have HCN. We're gonna have H plus. And we're gonna have Cn minus. The initial HCN concentration is this. It's a 0.100 molar HCN. So that's my initial concentration. No H plus, no Cn minus. Since I have no initial concentration of these, the reaction has to go right to reach equilibrium. I actually used the wrong arrow there. Sorry, guys. Has to go right to reach equilibrium. So the HCN is going to go down by X, and the H plus and Cn minus are going to go up by 1x. And now my E column, combine those, 0.100 minus X, X, and X. So hopefully you can see, right, how much more of a pain, we're not done. But hopefully you can see how much more of a pain these weak acid problems are. If that was a strong acid, say that was HCl, it would fully dissociate. That's the H plus ion concentration. But since this is weak, we got to go through all this because we don't know how much H plus it produces unless we go through this entire process. Now what we do is, since we have these equilibrium values in terms of X, we can now plug them into the mass action expression with the equilibrium constant, the acid dissociation constant, right? And then hopefully we can make X small. So let's try that out. So what do we end up with? We end up with Ka 4.9 times 10 to the negative 10 equals X times X, X times X over the HCN, which is 0.100 minus X. Now, okay, again, if we can't get rid of this X, we are going to end up having to do the quadratic formula, which would suck. Okay, so we want to see if we can get rid of that minus X. Then we can avoid the quadratic. So we're going to take our smallest initial concentration, divide it by the constant, and if it's greater than 500, we can get rid of that minus X. So let's check it, right? So 0.100 divided by 4.9 times 10 to the negative 10. Now, folks, you can put that in your calculator if you want, but 0.1 divided by 0.0000000049 is greater than 500. Okay, it's going to be like a bajillion, right? Or a billion or something, right? So that is definitely greater than 500. So X is small. And if X is small, you get rid of that minus X, man. And that is like the most beautiful feeling in the entire world. So great. So now we start doing regular old algebra. Okay. We're going to multiply both sides by 0.1. So 4.9 times 10 to the negative 10 times 0.1. That's 4.9 times 10 to the negative 11th. And that's going to equal X squared. And now we can take the square root of those values. X is 7 times 10 to the negative 6th mole. So what did we just get? Well, we got, at the end of the day, we wanted the H3O plus ion equilibrium concentration. What is the equilibrium H3O plus ion concentration? You just got it. It's X. It's 7.0 times 10 to the negative 6th molar. Now, we can get a pH out of that rather easily. Okay, how do we get a pH? Well, pH is the negative log of that equilibrium H plus. So now pH equals the negative log of that 7.0 times 10 to the negative 6th. And that's going to be 5.15. 5.15 is the pH.